Hello, everyone. Good evening, good morning, good day, wherever you are in the world. Greetings from California. That's where I am. I'm Marina Bosi, as Leonardo mentioned, from Stanford University in Northern California. I'm also a founding director of MPI and the chair of the content-based audio enhancement development group. And that's what I would like to talk about tonight for me, this morning for you guys. The accomplishment we made in the last couple of years, which included this first version of the specification and the second version as well, which concluded not too long ago. Before I start, I want to remind you what Leonardo already showed you, which is kind of the baseline for everything we developed within MPI. As you can see here, we have a bunch of green modules that we call AI modules, and those are kind of the, if you wish, the Legos that we kind of put together. We don't specify the internal working of the AI module. We do specify the function they carry out and input and output. As if you're looking at the bigger picture, then we have what we call the AI workflow, where we specifying inputs and outputs. And around it, there is a whole AI framework, which my colleague, Andrea Basso, will describe more in detail later on. But basically, that's how we communicate, how we govern what we produce through the MPI store, for example, which is responsible, among other things, about registration of the different implementations. So that being the case, I'm going to show you a couple of block diagrams that will reflect the work we did in the past couple of years. So the whole idea behind this is that we want to have an open market of AI modules. So we don't just look at one implementation, a specific implementation, but a whole open market supporting the development of the AI industry. So along those lines, I'm dealing mostly with audio, and basically the idea is that MPI-CAE, which stands for Content-Based Audio Enhancement Development Group, the work we did aimed to improve the user experience using context information to act upon the audio content. And as Leonardo mentioned, version 1 was adopted by IEEE as IEEE 3302. So we address different scenarios in the home, in the studio, in the classroom, and so on and so forth. But the whole point is that we are trying to maximize and optimize the end user experience when it comes down to audio. So currently we have identified 4 different use cases, which are standardized in version 1. And these use cases we're going to be examining, and I'm going to give you a couple of demonstrations throughout this talk. These 4 cases are emotion-enhanced speech, audio recording preservation, speech restoration systems, and enhanced audio conference experience. So starting with the first use case, oops, sorry. Here we have the emotion-enhanced speech. Speech is not just made of words. There are emotion behind it. And especially when we talk to an avatar, we would like to have more and more the confidence of emotions embedded in the speech. So this is a use case that enables the conversation of individual and the conversion, of individual emotionless speech segments into segments that have a specified emotion. And this emotion can be expressed as a tag. So we have a list of emotion from which we can select a specific one we want to implement, or can be derived by an utterance where we choose a specific model and we detect a certain feature and we want to incorporate into the synthesized speech. So what you see here is kind of an application of the AIF workflow that I showed you before. And here we have an input and an output, and the output is the speech with emotion. In the input, we have the emotional speech, which then will be incorporated with the emotion, but also we have the different ways of incorporating this emotion. In the upper part, we select a model utterance that reflects the specific emotion we want to imitate. And based on that, we recreate that on the synthesized speech, and that gives us the speech with emotion. On the lower part of the diagram, we have a different way of doing it, which is by looking at an emotion list. So a long list of possible emotion, attitudes, if you wish, personal states. And that also would be incorporated in the emotionless speech to create the speech with emotion. So if I'm doing okay on time, I'm going to show you a couple of demonstration. On the left side, I'm going to play the original recording done by an actress, Jenny. And on the left side, what we standardized in terms of the EES use case, and the demo was provided by speech morphing. So here is the original recording.
That really is remarkable. I never would have imagined that was possible.
And this is the synthesized version with the emotion that was in the original recording.
That really is remarkable. I never would have imagined that was possible.
And here is another example.
Are you absolutely certain that you've been taking the medication as the doctor prescribed?
And this is the output of the EES.
Are you absolutely certain that you've been taking the medication as the doctor prescribed?
Given that I have a very limited amount of time,
that really is remarkable. I never would have imagined that was possible. Are you absolutely certain that you've been taking the medication as the doctor prescribed?
If I can move on.
Are you
here.
absolutely?
Okay, great. So moving on, we're looking at the second use case that we standardized, which is the audio recording preservation, ARP. And the idea that we have is so much cultural heritage, which is stored in a way that can be lost because of the short-lived typical of some of the medium in which was original recorded, and or completely degraded so that we cannot enjoy it anymore. So the idea is that we would like to preserve and access analog recording that are often not sustainable as they are. So we use artificial intelligence algorithms to not only preserve, but also digitize, which is not a neutral process. Also, the AI is used to drastically reduce the costs related to analysis, restoration, and preparation of the final product. As a use case, here we have the specific case of a magnetic tape, open reel magnetic tape. So in the input, we have the digitized version of the audio file, the preservation audio file here, and also a visual file of it, so audio visual, because some of the let's say of the irregularities, which are problems in the original version, can be reflected in audio, but also can be visualized, like, you know, slices that were not done properly, or corruption of the medium, or sometimes actually things that the composer himself or herself wanted to be included that were annotated on the tape. So those are actually important part of the preservation process. So given that, we analyze the audio from the audio point of view, but also from the video file. We identify irregularities, and based on AI, we classify the different type of irregularities, and based on that, we restore the audio to what was meant to be the original intent of the composer or of the producer, and so on and so forth. So all that gets packaged, and at the output, we have two copies of the file. One which is just the access copy, where we can just listen to the file, where maybe even some noise reduction was applied. And the preservation master file, which include the original, the irregularity files, irregularities images, and of course, also the access copy. So those two files are going to be produced in parallel, and one to be enjoyed and one to be preserved for the long term. So moving on, then
Marina, I remind you that you are half your time.
Thank you, Leonardo. Just very briefly, I wanted to mention, since I have the opportunity, that AudioInnova, who was the main proponent behind the ARP technology, was awarded the prestigious Cannes Neurons 2023. The World Artificial Intelligence Cannes Festival, which is a remarkable thing because this award honors the most innovative and impactful AI project in the world. And that was done in recognition of the work on the development of the MPI-Chi ARP. So congratulations again to the AudioInnova team. I have to say this, I'm very proud of the team that worked on this in the Chi DC. One more use case, somewhat related, but somewhat different in that the speech restoration system addresses also inaccuracy, but instead of trying to reconstruct them, completely substitute a resynthesized version of it. I'm not going to go through details because I'm afraid I'm running out of time, but I would like to do a brief demo if I may. So here is the demo. I think it's self-explanatory, but if you have questions, please, by all means, feel free to ask them.
Hiding within the long grass. They have chicks in a nest nearby.
So you notice the bad segment in the middle.
Hiding within the long grass. High above, a pair of imperial eagles are keeping watch. They have chicks in a nest nearby.
Where the segment was synthesized based on the model of the voice that was currently used.
Hiding within.
Currently used in the segment that was intact. So the last use case that we have for the enhanced audio conference experience was proposed in the middle of COVID. So this was something that was sort of close to our hearts because we were doing Zoom meetings, as probably now, all the time. So having some problems in terms of audio, not being able to distinguish speech and so on and so forth was something that was kind of an interesting and very useful problem to be solved. So here we have a use case which is rather complex. We start with an input that comes from a microphone array. A minimum microphone array is of 4 microphones, typically 16 or 32 is more desirable. And the audio recorded by microphone array gets inputted into a time to frequency domain transform. The transform audio, which is multi-channel because we have multiple microphones in the microphone array, gets analyzed, and the spherical harmonics decomposition is taking place here. The spherical harmonic decomposition is used both to create the audio scene, but also to separate the different speech sources in the audio scene. So at the output of the speech detection and separation, we have the speech in the frequency domain and the audio scene geometry of the environment. If needed, there is a noise cancellation stage here that not always gets applied, but when necessary, in order to make the speech more intelligible, gets applied. And finally, we have the denoised speech, which is transformed back into the time domain and packaged with the microphone array geometry, so that can be reproduced correctly in the on the other side, and the audio scene geometry. So the output, the overall output of the workflow of the enhanced audio conference experience is the multi-channel audio, which reflects the number of sources detected and separated, plus the audio scene geometry that was computed. So, again, if I may, Leonardo, you're going to be interrupting me if I'm running out of time, but this is kind of a preliminary example. I mean, the EIA is meant to be running in real time, and we have reference software that will be available in the next couple of weeks. Hopefully, I'm actually really counting on it. But what I'm showing you is a preliminary demonstration of the source separation, both in an instance where it was a quote unquote, an ideal environment with no reverberation, and another one where we had reverberation that would make the speech almost not intelligible. So this is what the microphone in the simulation would record here.
In the course of a December tour in Yorkshire, I rode for a long distance in one of the public coaches on the day preceding Christmas.
The simplest method
The
is
coach
to
was
mix the
crowded,
mix.
but
For those of you involved in audio coding will recognize some of the excerpts from the Squam disk that we fought so much in the development, but here are they separated.
in the course of a December tour in Yorkshire, I rode for a long distance in one of the public coaches on the day preceding Christmas. The coach was crowded, but
This is the second source.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so. The simplest method is to mix the medicine.
And the third component.
Le front froid qui traverse le pays d'est en ouest provoque un changement de temps et une baisse sensible des températures.
There are
En fin de
instances.
semaine,
Yeah, so there are instances where actually the environment was not ideal, and this is an example.
In the course of a December tour in Yorkshire, I rode for a long distance in one of the public coaches on the day preceding Christmas.
The simplest method
The coach was crowded.
And again, we can separate and remove some of the reverberation, which was not desirable.
in the course of a December tour in Yorkshire, I rode for a long distance in one of the public coaches on the day preceding Christmas. The coach was crowded.
And this is the other component.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so. The simplest method is to mix the medicine.
And again, this is a preliminary demo, as I said, hopefully.
I rode for a long distance in one of the public coaches on the day preceding Christmas. In the course of a December tour in Yorkshire,
Okay. As I said, a reference software for this use case will be available very soon. One last thing I wanted to mention is version 2. As Leonardo said, we just finished this. And version 2 is, if you wish, is an extension with respect to the audio scene description. Here we have a more generalized algorithm that is able to distinguish in between different sound sources, not just speech sources. I'm not going to go through the details because I'm running out of time. But yeah, so basically the idea, not just speech objects, but also sounds are recorded by the microphone array, the multi-channel audio scene description, and the output is the speech or audio object with the location and the audio scene information. So this is regarding version 2, which, as I mentioned, is a composite IAM, which is adopted, for example, in CAV. Leonardo mentioned the connected autonomous vehicles standardization and other applications within MPI. So basically, again, the goal for MPI Chi is to improve the user experience using context information. we specified 3 use cases: the enhanced emotion-enhanced speech, audio recording preservation, speech restoration system, and enhanced audio conference experience. And this is also an IEEE standard, IEEE 3302. And we also have the technical specification version 2, which is a more sophisticated version of the audio scene description that can be used in different type of applications. So I would like to conclude thanking the team. Really grateful to have had a chance to work with wonderful people, Sergio, Mert, Nadir, Hussein, Nicolò, Mark, and Fatih. Thank you for your invaluable contributions. And please join the fun. We are having fun, and I hope you consider contributing to the work of MPI. And thank you so much for your attention.